Okay, thank you, Lucian, for your introduction. Also, thank you, the organization committee, to including me for such a wonderful event for dog. Okay, so today, basically, I would like to talk our new work. So the reason I chose this, then you will see in a second. Okay, so that's I cannot move in my, okay. So this is outline. First, I will give some introduction about dog and myself. Then I will introduce the problem we are trying to tackle. Then I will show you some existing method. And the most important one is the Pippenger bucket method. Then I will show our construction and the benchmark and the optimization, further optimization. Okay, so I came Waterloo in 1998. From University of Southern California, worked with Saul Galambo. And basically, Doug brought me to Waterloo as his postdoc. So although it's a very short time as Doug's postdoc, about maybe 4 months, then after that, Doug and I become a colleague and friend for those many years. So this is our first work. Yeah, so when I joined Waterloo in 1998, I think in August. So basically you see Tom Burson visited me in China in 1995, because then he brought me Doug's book. I think Doug's book just published, he said maybe 2 weeks ago. Okay, so that's the first time the Doug. Then after I joined Waterloo, then we found that, okay, you see, Waterloo we always think is the birth of the ECC. So we want to look at how we can generate a random bit from the elliptic curve. So this is the first work we did. Then we presented in the SEC 1999. Okay. I think also the SEC 1999 also in Waterloo, I think. Then after that, I think Doug and I co-supervise the students, Kongming Ku. So basically, I'm in the ECE department, Doug in the computer science department. Only during that time, Kongming was in the department of C&O. So 3 of us basically in the different department. I remember it's just a wonderful time. We met once each week, but it's a very long meeting for that, at least 3 hours. I believe this work is some new calculation of semi-bent and bent functions on finite field. And the Doug come out to the very genius idea. Basically, our criterion here is using the coding method. So if you're interested, please look at this. Okay. Then in 2010, Doug and I, together with Alice, then we organized the SEC conference in Waterloo. This is a very fun experience we two together got the SEC. I think in that year, SEC was so rich because each of us got some fund from our own department. Then we also got from outside. Okay, then, so this is, I think there's many other things I may not have much time to share with you, but you already see so many stories now. Okay, so now I will turn my gear to what the work I would like to present. So this is more like the hook progress report. Okay. So we wanted to look at how we compute the sum of multiple scalar multiplications in elliptical group. So this termed as multi-scalar multiplications. So basically, it's we compute endpoints. So P1 and Pn, those are fixed points, not the random point. And the AI, A1 will be their scalar multiplications. Okay, I'm sorry, so I guess. Okay, so currently, for example, a lot of methods for speed up this computation, for example, just one term, one scalar multiplication for the Diffie-Hellman keys. And for digital signature, you just heard the Berkeley's talk. So basically, it's computed the sum of the two scalar multiplications. Okay, so the question we want to ask is how about larger n? For example, n in this range, at least 2 to 16, or of course as large as possible, but possibly we can do it up to 2 to 23. Even that 2 to 23 may not have many applications, but greater than 2 to 16 has many applications. Okay, so then this is our motivations. Basically, in the zero knowledge, they call the zero knowledge succinct non-interactive argument of knowledge. So that's ZK-SNARK. So in the ZK-SNARK basically has the two types of sightings. One type of sighting is with trusted setup. So the trusted setup basically is using pairing-based cryptography. So in those settings, and the multi-scalar multiplications dominate the entire time complexity in those ZK-SNARK schemes. Of course, another type is without trusted setup. So in this, our problem comes from with those ZK-SNARK with trusted setup. Okay, for example, in the zero cache. So basically, those are the proof systems. So what do they want to prove? For example, you have a hash function 256. Then you write hx equal to y. Then you want to prove your computation hx equal to y is correct without knowing pre-image x. How you can show the any verifier, your computation is correct without showing the x. Okay, so in the SHA-256, I'm sorry, I think, do you see my slides in the right size?
I think it got zoomed bigger.
Yeah, so maybe okay.
Now it's fine. Yes.
Okay, thank you. So those proof system, basically you expand the SHA function into a circuit representation. And in the circuit representation, usually we only count multiplication gate, not counting the addition gate. So in this case, SHA-256, if you just run once, it's about 32,000 multiplication gate, or is in this case is AND gate. Okay. However, you know, in those blockchain, then they using the Merkle tree. Also, Burke also just mentioned the Merkle tree. For example, even you have 64 leaves, then you get the Merkle root. Then you basically run 64 times of your hash function. Okay, so your circuit will be the nested hash function. So those circuit is very, very big. Okay, so the number of the multiplication gate in those circuit basically is number of the scalar multiplications you want to add together. So that's the problem we try to tackle. Okay, so there's many existing methods because you see ECC is so popular. Then it's in the IEEE standardization, in the list recommendation, in basically everywhere. So for the small n, then there's many known methods. And for example, binary method, doubling and addition, then you could also have construct some number systems using some basic digit set, or you change the basis using multiple base number systems. Then you also could use some addition chains. Then there's many those works about the addition chains. Okay, so those is for small n. So usually n is maybe 3 or 4, because I guess is no application require the big n's. The digital signature only the n equal to 2, so that's about the application. Then here comes what's called the Pippenger's bucket method, and its variant. So this is one you can do small n, also can do big N. Okay, so let us look at this in more details. Okay, so for the large N, so that's the about in this ranging. That's the or you write the 10 to 5th or to bounded 10 to 7 in this ranging. So we look at those literature, we found the Pippenger's bucket method still state-of-art algorithm, which means they are most efficient implementation method. Look at the practice, like those SNARK-oriented implementations. For example, the zero cache or Zcash, Topper-Planck, Bellman, all of those blockchain cryptocurrency, they basically implemented their SNARK using Pippenger's bucket method. Okay. So let's look at what is the idea in Pippenger's bucket method. So if we wanted to compute, we have 13 points, then which means the sum of 13 scalar multiplications. Okay, so if you general computation, then you need to do at least possibly around 12 additions, right? So then we look at idea of the Pippenger's method. So basically, he will sorted this 13 points into 7 buckets according to the scalars. So scalars 1, scalar 2, scalar 3, all the way up to 7. Okay, because we look at the 7 is the largest number here. So for example, coefficient 1, then we have the P6, that's here. Then we have the P11, so we put here. And the 2, coefficient 2, I'm sorry, I'm so sorry. I don't know what I touched. Okay, I don't touch my computer now. Okay, so then, let me see. So if that's the coefficient 3, then we also have 2 points. So now we will compute those inset points. So those we call the bucket. Okay, so those inset, inset point bucket, then you compute those. After that, those results with coefficient 1, I call the S1. With coefficient 2, I call the S2, and so on. So last one is 7S7. So now, then after I have those bucket value computed, then I will do this. So this we call the accumulation algorithm. Okay, so for the accumulation algorithm, then you can compute it through those more like the Horner's algorithm. Okay, so that's you do this triangular ways, then this is you computed the 7 times, so that's the 7S7, and so on. Then you get the S1. So that's the accumulation algorithm to compute this accumulated sums. Okay, so that's the idea of Pippinger's bucket method. For the Pippinger's bucket method, basically you do not need the pre-computation and the storage. Okay, so in this way, then we will do, if we have a bucket there, then we will have 6 additions, because that's our bucket, each is just 2 points. Then we will have the accumulation, which is 12 additions. So we total, including scalar multiplications, we only have 18 additions. Okay, okay, so that's the Pippinger's method. Okay, so this is the case if your R, which is the order of the elliptic curve, if that's small, then you can do this because those AI is bounded by R. Okay, so in this case, all of those points can be sorted into R1 bucket according to the scalars. So now a scalar is from 1 to up to R minus 1. Okay, so in this case, then we know we can do the n minus R plus 1 additions for compute all bucket values. Then accumulation method will be the 2 times R minus 2. So this is number is in total of the additions we needed to compute this multi-scalar multiplications. Okay, so that's the Pippinger's method. However, if that's R is big, what we can do? For example, for the BLS 12381. So even this 381, they only provide, I think, a little bit less than 128-bit security. Okay, so in this case, R is approximately to 256. So which means they have 255 bits. Okay, so in this way, then we will represent the scalar in a query number digit. So which means each scalar we represented as the query numbers. So now our MSM can be rewritten as this form. So this is becomes like you have the NH point, then you have the size will be the Q instead of R. Okay, so that's the Pippinger's first variant method. Okay. Then, so in this case, then you need the pre-computation now. So basically you pre-computed those points. Okay, how many pre-computation? Then basically is NH pre-computation. Okay, so then those points you need to be stored. Okay, so now then you have n Q minus 1 bucket in total, and this many NH plus Q minus 1 additions. Okay, so that's the first variant. Then, if they properly choosing the bucket, then they could further reduce. For example, then they were divided the bucket into the 2 different things. So one we call the multiplier side, another we still keep the name called the bucket. Okay, so if we can write the AIJ is equal to product of one element from multiplier side another element from bucket set. Then our sum can be rewritten in this form. Okay, so in this form, then we need to do how many pre-computations? We need to do NH multiply number of the points in the multiplier set. Okay, so then in this case, we will take about the NH plus cardinality of bucket set. Okay, so that's how we divided those computations into the two parts. So this is called the bucket method variant 2. So using the multiplier set concept, then variant 1, basically multiplier set only has one element, and the bucket set will be those elements. Okay. So then for the variant 2, the multiplier set basically two elements, 1 and -1. And the bucket set only half of the Q values, so from 1, 0, 1 to Q divided by 2. So in this way, it takes about the NH plus, I'm sorry here, Q over 2 additions. Okay, so that's the variant 2. What's our goal? So our goal, we try to construct the bucket which has a size about the Q over L. So in this way, then we can get that computation is about the Hn, that's the common term, we do not touch. And this term becomes Q over L. Look, see, the variant scheme I just introduced, basically here, L equal to 2. So we ask what we can do for this L. Can we up? Basically, in someone conjectured, they said maybe 4, but we break this boundary. We can do any L basically. However, L depends on the Q and the H. So some L are bad. We only take those good L's. Okay, so this is our new construction. Then we will have take our Q is particular number, which is the prime, such that the 2 is a primitive element in GFQ. And our L and H will be bounded by those conditions. So our multiplier site looks like this. And our bucket side will be the union of the two subsets. Okay, so basically our idea is, so our idea for constructing, basically we observed this phenomena. So those, because we take the 2 is a primitive element, so then we can represent it as the power of the 2. So that's how we can construct our multiplier set and the bucket set. Okay. However, look at our bucket. Our bucket is a number. This one no longer consecutive. Compare with the known method, they always consecutive. But our bucket, the number in the bucket no longer consecutive. So we need a new accumulation algorithm. Okay, so then we get our results by choosing that multiplier set and the bucket set. And this is we need to do pre-computation, also need to be stored. How many points? Ln times H. Okay. So for the L equal to 12, basically we instantionize the BLS 12 381. So our new construction compared with the known one get the improvement from 5% to 13%, which is depends on the number n. So this comparison we compare with the most efficient one, which is the Pippenger's bucket method variant 2. Okay, so those are some benchmark for our instantiations. So we start with n equal to 2 to 16. So we choose our L always 12. So that's different Q, different H. And those are different number of the additions we calculated. But you look at the figure, then we compare with the variant 2. So basically, you look at the 2 to 17 is about 13, more than 13% the improve compared with the Pippenger variant 2. So basically, for the hash 256, so it's about this. So which means for the zero cache, if we replace their Pippenger's implementation by our new implementation, then we could get a 13% improvement compared with their current performance. Okay. Of course, we could do more optimizations, but I won't show you in more detail now. But anyway, this is our results. So we can, so this SNR, so which means the sum of the n-scalar multiplications can be computed using this, at most, this many additions. And with the pre-computed point is ln times h over 2. And the q is the prime, and the 2 is the primitive element of modular q. That's the what we got from this work. Okay, and this is the paper we submitted to the CHES. I do not know, but and if you have a question, and I think my student Guang is in the audience. But anyway, happy birthday, Dad. Okay, I finished my talk now.